Hi, I'd like to give you a little bit more information about the workshop last week and feedback to you some of the problems people are having to look out for in compendiums so that you're going to be better at giving the peer review. So here's a couple of histograms and I'm going to show you some comments as we're going along. So this person believes that 15 bins is the best representation of the data as the shape is close to what a histogram should look like for a normal distribution. Well, that's sort of assuming that the purpose of doing a histogram is to make it look like a normal distribution. That's not what the purpose is. It's to give you an accurate representation of the distribution. And that distribution doesn't have to be a normal distribution. Okay. Next comment, 19 bins were chosen as a variation of the bin size. But the bin size was too narrow and potentially important information may be just due to random variation. Sounds plausible, but when you look at it carefully, the logic of what this is being said here is not totally obvious. Certainly if the bin sizes are very narrow, then you'll only get one or two items in a bin and many bins will be empty and you'll get a very sort of strange looking thing. But what is it that what is the potentially important information that they believe is being lost, and what is the link to random variation? So they're struggling to grasp the concepts there. Okay, so you have to unpick that a bit for them. Okay, the bins were changed to 30. I felt it was the best representation of the data as it's the most evenly distributed. Again, this is a comment about what the appearance of the histogram should be. The purpose is not to change the bin size until it has a good appearance in itself. It's so that it has an accurate representation of what you think the underlying distribution is. And in this workshop, we're comparing the histogram appearance to the density plot appearance, again trying to get those two things matched to some extent. Here's a case where if the bin size is quite small, so there are a lot of bins, okay, this person has said 30 bins does not make the sample look like it lies close to the normal distribution. That's the business again of thinking the histogram is supposed to make it look like a normal distribution, okay, which it isn't. And it's made the data look like there are far more outliers throughout. So I think they're pointing at the spiky appearance of the data, but they're not outliers. An outlier is something that is uncharacteristic of the distribution. Okay, so typically these are items that lie far away from the typical values towards the centre. So this has got a value at the centre which is something like 80 or 90 or something like this. Okay, so the outliers would be the extreme values. Okay, things that are like way down below 60 or above 110. Okay, and then they've referenced to the QQ plot. So they're trying to make a link to the QQ plot, and there is a link. Okay, but it's not apparent from this comment what the link is. Here are the two things we've been looking at to characterize data. The density plot is like a modern version of the histogram, okay, and I've set it up in this particular workshop class so you don't have to manipulate characteristics of the density plot, and actually you don't need to, because it works them out for itself from the data that you give it, okay, which is not usually the kind of thing for the histogram, not quite so much. This business of a kernel, this is just sort of a mathematical construct in the middle which gives it this smooth appearance. Okay. Sometimes students will answer what they think the question is and not actually the actual question. Okay, so these numbers, the bins, show a change to the histogram but not the density or QQ plot graphs. Therefore you cannot pick which density graph is the best. But actually that's not what the question was about, is it? We asked to choose the histogram that best represented the data distribution based on the information in the density plot. Okay, so you manipulate the histogram to give you the best representation of the distribution as it appears to have been given by the density plot. Okay, a little bit about QQ plots. Now these are a graphical method for testing normality and assessing whether or not a data set is approximately normally distributed. Nothing is ever perfectly normally distributed except a mathematical function. Okay, but this is a way of comparing an actual distribution, the sample quantiles on the left, with the theoretical quantiles derived from the theoretical distribution of the normal distribution. Okay. So observed value for each score is plotted against the expected value from the normal distribution, sort of, and if the values lie close to this red line, it's suggestive of a normal distribution. But here's some typical comments. Some of the points are not on the line, but the majority are, therefore the assumption of normality can be applied. Well, actually, I'd guess looking at it from this, the majority aren't on the line, and anyways, it's not about being exactly on the line, okay? So they're close. Here's another one. The QQ plot shows the data is normally distributed as the data is clustered around the normal line of distribution. Sort of, but they're missing the main characteristic here. Let me see. The main characteristic that shows that there's maybe a deviation from normality is that actually this clustering around the line is not that apparent. There seems to be systematic deviations away from this red line at the extreme. So this is an indication that there's something to do with too many outliers in the distribution. Okay. So what was a proper normal QQ plot look like? Okay, so if you really were sampling from a normal distribution, here's 4 examples which are taken from a computer simulation where the computer is choosing from a mathematically perfect normal distribution, and it still doesn't come up with dots that are exactly on the red line. Okay, so you're looking for things that are approximately along the QQ line of normality. There will always be some kind of sampling variability about the line, and you never get an exact answer. It's not a sort of a red flag that comes up and says, oh, this is definitely not normal, or a green one that says this is normal. Okay, it's something that it's a visualization, but it's a very powerful visualization. It's very widely used in statistics. Just how much of this wavering around the line is acceptable, okay, is difficult to say. It depends to an extent on the size of the sample and things like this. But once you've seen a few of these different things, then eventually you start to get a feel for whether or not you should be concerned to investigate further the normality of your sample. Okay? So there should not be any systematic manner in which the points deviate from the line. Now these ones have been taken from a population which is negatively skewed, and so it should resemble the left-hand top of an arch, if you can imagine that. In fact, if you look at what these ones at the bottom, it's very clear what we mean. How bendy it is depends on how skewed the distribution is. If it's not skewed at all, then we're back to a normal distribution, but this is very slightly skewed. Okay, and as we get more and more samples, so I'm not changing the skewness here, it's just simply sampling more, and the more we sample, the more likely we are to get sample points that help us characterize the distribution better, and then we pick up more closely on its deviations from normality. So you can see how the level of skewness in the population is reflected in the QQ plots of the sample. Okay, so these ones are good evidence of not normal distribution. Here's some that's from a sample that's even more skewed. You see, very easy to pick up what that is. So, summary of mistakes people made. Belief that the purpose of the histogram is for making the data look normal, as opposed to illustrating what the data distribution is. Okay. Thinking that increasing the bin number is increasing the variation of the data. Okay, it's not. It's just a way of categorizing the data differently and illustrating it. It's not actually changing the data at all. It's visualizing it in different ways. This is why it's a sort of sensitive topic to get used to. Okay, so you've got to be able to produce a visualization which accurately represents the underlying characteristics of the data that you're trying to communicate. The histogram appearance is rather spiky when you've got lots of bins, but very few students describing the spread of the distribution spotted this or thought it was odd. Okay, and it is. It shows that the data is clustered at points, and it comes about because the IQ scale is in fact binning the scores. Okay, so because you can only have certain values, then lots of people will, they're integer values, so people will have 91 or 92 or 93, but they can't have 92.5 or 94.75 or something. And so you get this sort of clustering thing, and you can see that in the QQ plot as well. You see these little step type fares instead of this sort of sprinkling effect that you'd get if the scores were coming from a real number distribution. QQ plots, copying my notes into your compendium isn't quite good enough. We want you to do it in your own words, and also you've got to be very clear about what the two axes on the plots are. You have to read up on your notes about this, and the reading in Dancy and Reedy or the Howell book. Okay, and I think I've got some notes on it as well on the website. And also you've got to be quite sensitive, as we saw a few slides ago, that just getting the things near the line is not quite good enough. Okay, because all the points are going to lie on the line. In fact, the QQ plot is constrained to pass through the point 0, 0. Okay, so it will always go through the middle. Right? And you have to look out for comments about the abnormality, as it shows up mostly towards the extreme parts of the distribution. Okay, so this business of it curving away in a systematic manner, the cluster of points on the QQ plot curving away from normality. When we come to the peer reviews that you need to do, here's some examples of good and bad feedback. Okay, simply answering the question directly, this is correct. It may well be correct, but we need to be able to dig into it a bit more. A much better example is given underneath here, where the person is evaluating the effort and the quality of the review that's being given, and actually giving some further tips about how the numbers and things should be represented. In this case, only 1 or 2 decimal places is thought to be a more appropriate way of reporting the values. Question 2. The author has demonstrated good and bad choices of the bins, but failed to say how many bins have they used. And for the same review, remember these are for the same review assessed by different reviewers, and it turns out the author has not labelled the number of bins that they've used. Apart from this flaw, it's a good explanation and bad choices of good and bad choices of the bin numbers, and demonstrates the ability to relate how different bins can facilitate or hinder investigations in research. So that's giving a little more insight again into an evaluation of how well the task has been performed in the review. Okay, so try and pick up on things like that. Question 4. The explanation is sort of correct, but it's vague in terms of why the author believed it to be the case, as opposed to a much more full and insightful review. Although the answer is correct, that the distribution is not normal, the author is talking about this being above the mean value. Okay, but this is not the case, and he explains why. So identifying shortcomings or misunderstandings, and then also supplying corrective information is the way to go about things. And that's all for my review this week. Thank you.